Alright, so in this chapter, we are going to start talking about probability. Okay? And the first thing I want to talk about is a review of randomness. So, in a random event, I think I went over this in a previous chapter, random event is not a total chaotic type thing where anything can happen. Randomness is defined as we know what could happen, but not what will happen. So we have a dice, alright? We go to roll the dice. We know what could happen. We could get a 1, 2, 3, 4, 5, or 6. But we don't know what will happen when we roll the dice. Okay? Same thing with the roulette wheel there. We spin the roulette wheel and we put the ball in. And I believe we have 40 numbers in there, or however many numbers there are. Okay? We could have the 0 or the double 0 come up. There's the 0 right there. There's the double 0 right there. Okay. Or we could have any of the other numbers up. We could have red or black come up. Okay. We could have green come up because the 2 zeros are green. Alright, so we can have a myriad of things happen. We know what could happen in advance, but we don't know what will happen. Okay, so that is all about randomness. Next thing I want to talk about is this concept of the law of averages. And on the screen it says the law of averages will clobber you every time. Okay? And what the law of averages says is that things are due to happen. And it's a pretty common thought process. Okay? So we go back to our roulette wheel problem and we say, we sit there and we watch it 10 times and red comes up 10 times in a row. And we say, okay, well, black's got to come up now. And we're going to put a lot of money on black because black is due to come up. And if you think like that, you'll lose a lot of money. Okay, because black is not due to come up. Okay. I believe there are 19 blacks and 19 reds and 2 greens. So the probability you will get a black on any roll is 19 out of 40. And the probability you will get any red on any roll is 19 out of 40. The roulette wheel doesn't care what happened in the past. Okay? The probability doesn't change. Every time you spin the roulette wheel, black has a 19 in 40 chance and red has a 19 in 40 chance. We roll the dice. We roll it like 20 times and the 5 doesn't come up. Get everything but a 5. Oh gee, 5 hasn't come up in a while. I'm gonna bet on a 5. Oh no, 5's not due to come up. The next time you roll the dice, there's a 1 in 6 chance that the 5 will come up again. Okay, the dice doesn't care what happened in the past. Okay, so this whole thing about the law of averages, statistically speaking, is a false premise. Okay, and what we like to think of is what's called the law of large numbers. So in front of you is a graph of flipping a coin. Okay. So let's say that this is the percentage, of heads that have come up every time we flip the coin. So what happened is the first time we flipped the coin, we got a heads. Okay. And then apparently we got a lot of tails because by the time we were on like our 3rd roll, we got 2 more tails, so we only had like 33% heads. And then heads started coming out a lot again, and we went up over 50%. Then we got a bunch of tails. Then we got more heads, tails, more heads, tails. Well, what happens down here is as we continue to flip the coin in the long run, okay, the probability that we get a heads on a coin is going to be 50%. So the long run frequency occurrence is 50%. So what happened here in the beginning? All this in here. Well, those are called short-term anomalies. And statistically speaking, short-term anomalies happen. Okay? You probably going down in the gym and maybe your friend went to the foul line and sank like 10 in a row. Okay, but your friend's not a 100% free throw shooter. Okay, or you go out and you're playing a game and all of a sudden your friend or you, quote unquote, get hot. Well, what happens is in the short run, these types of things can happen. So when we're playing our roulette wheel here, we're not disturbed by the fact that if we were to sit there and watch it go 10 times and red came out 10 times, that's fine. But that doesn't mean that that's going to continue indefinitely. Now, if I spin the wheel 1,000 times, the probability of red is going to be pretty close to 50%. It's going to be 19 out of 40. It's just short of 50%. And if I was to spin it 10,000 times, it would be even closer to that 49 or 50%. Okay? But when we do things in the short term, the frequency of occurrence doesn't always match the probability, and that's okay. But that doesn't mean that the wheel is going to self-correct itself. What it means is that in the long run, if we keep doing something, okay, the frequency of occurrence is going to approach the probability of it happening. And that's what happens when we flip the coin. We keep flipping the coin, keep flipping the coin, keep flipping the coin. Guess what? Heads comes up 50% of the time. Okay, you may flip the coin 5 times and get 5 heads in a row, but if you flip the coin, keep flipping the coin 500 times, it's going to wind up getting to its long-term frequency. Okay, and that's going to be at 50%. So you need to be able to distinguish between these two concepts. This law of averages, that things are due to happen, is not a statistically sound thought process. Things are not due to happen. And this whole thing about law of large numbers, things are going to happen as their long-term frequency happens. Okay, so in the long run, things are going to kind of correct themselves out. Doesn't mean that things are due to happen. Just that in the short term, anomalies happen. In the long run, the long-term probability is going to happen. Okay, independent events. Independent events are a type of compound event where the outcome of an event does not affect the probability of any other event. So if I roll a dice, okay, I was to roll a dice, whatever I get on the dice, okay, on the first dice, if I was to then roll another dice, what I got on the first dice does not affect what's going to happen on the second dice. So those events are called independent events. Okay, so when one thing does not affect the other, those are independent. I'm going to draw a card from 2 decks. So I'm going to draw a card from this deck. Now, does that affect the probability of me drawing an ace from a second deck? Well, no, it doesn't. What happens in this deck has no effect on what's going to happen in that deck. So those are called independent events. Okay. The next thing is called disjoint events. Now, disjoint events are when one thing happens, another thing cannot happen. So we have this bag of marbles here. I can pull out a blue marble, I can pull out a red marble, I can pull out a green marble. Okay? I cannot pull out a red and a green marble. Okay, there are no marbles in there that are red and green. They are disjoint. It's either green or red or blue. Okay, so those are disjoint. Okay, when you cannot have a combination of any of the things that are in there. It's one or the other, and that's it. Okay. Next thing I want to talk about is sample space. Okay. So sample space is just the outcomes that can happen from an event. So here's the sample space for a dice. We could get a 1 through 6. Here's the sample space for a deck of cards. Okay, so there's 4 suits. We got diamonds, clubs, spades, and hearts. Okay, I think I reversed clubs and spades, so that's okay. Okay, and each suit has an ace through a king. So there's 13 cards in each suit. There are 26 red cards, 26 black cards, and there are 52 different outcomes if you were to choose a card from a deck of cards. Okay. Sample space for rolling 2 dice. So if you were to roll 2 dice and add them together, here's the sample space. So there are 36 outcomes. Okay. Well, actually, there's 11 different outcomes. Okay. You can get a 2 through a 12. There are 36 different ways of getting there. There's only one way of getting a 2. There's only one way of getting a 12. You get a 1 and a 1 or a 6 and a 6. There are 2 ways of getting 11, 2 ways of getting a 3. Okay, you get a 2 and a 1 or a 1 and a 2, or you can get for the 11 a 6 and a 5 or a 5 and a 6. 3 ways of getting a 10, 3 ways of getting a 4, 4 ways of getting a 5, 4 ways of getting a 9, 5 ways of getting a 6, 5 ways of getting an 8, and there are 6 different ways of getting a 7. Okay? So that's the sample space for rolling 2 dice and adding them together. Sample space for flipping a coin and rolling a dice. By the way, what kind of events are those? Those are independent. Okay, why? Because if I flip the coin first, whether I get a head or a tail, does that change what I'm going to get on the dice? Well, no, it doesn't. The dice doesn't care what the coin did. They're independent. Okay, they're 2 different events. One does not affect the other. Okay, so there's 12 different outcomes. I could get a head in a 1 through 6 or a tail in a 1 through 6. Okay? So that's it. That's the introduction to this chapter, and we'll get into the notes. Alright, so let's start looking at some vocabulary from chapter 14. We talked about random phenomena. Okay, a random phenomenon is we know what could happen, but not which outcomes will happen. So when we roll a dice, we know that we can get a 1, 2, 3, 4, 5, or 6, but we just don't know which one we're going to get. Okay, a trial is an attempt of a random phenomenon. So when you roll the dice, that's a trial. The outcome is the value generated or result for each trial. So when you roll the dice and a 3 comes up, that's your outcome. Yeah. Probability is a number between 0 and 1. 0 is 0% and 1 is 100%. Okay, it's just as a decimal. So anything that occurs has a 0 to 100% chance of occurring. Okay, the probability that the sun will come out, the sun will rise tomorrow. Well, that's 100%. Okay, the probability it'll rain tomorrow. Well, I don't know, given the conditions, it's probably whatever 30% or maybe 0 because it's a perfectly sunny day. Okay, so that's probability. Law of averages. We talked about this. This is the do theory. We think that things have a compensatory mechanism. They remember what happened and things are due to happen. So we roll the dice 20 times and the 5 doesn't come out. So what do we say? On the 21st roll, the 5 is due to come out. Well, no, it's not. On the 21st roll, the 5 has a 1/6 chance of coming out. It doesn't care what happened in the past. Okay? So this theory is statistically erroneous. Or you could put the word wrong if that doesn't work for you. Okay? It's not sound statistically. Okay, the law of large numbers. Short-term anomalies get drowned out in the long run. Alright, so if we were to roll a dice 600 times, on average we'll get around 100, or the 5 will come out 100 times. Okay, each number would come out around 100 times. Doesn't mean it'll come out exactly like that. But let's say that in the first 20 rolls the 5 didn't come out. Well, that's okay. We keep rolling the dice. We roll it 600 times, the 5 will come out around 100 times. We roll it 6,000 times, the 5 will come out around 1,000 times. Okay, we may roll it 50 times and the 5 doesn't come out. We may roll it 50 more times and the 5 comes up 23 times. Okay, those are short-term anomalies, but in the long run, the 5 is going to come out 1/6 at a time. Okay, the long run relative frequency. Well, what does that mean? The relative frequency? It's just a percentage. Okay, so the probability of a 5, the relative frequency of a 5 coming out in the dice is 1/6, which is about 16%, close to 17%. So that percentage is going to come out in the long run. So long run relative frequencies of repeated events settle to the true probability as the number of trials increase. We keep doing something, it will go to its true probability. Okay. Independent events. The outcome of one trial does not influence or change the outcome of another trial. So flipping a coin and rolling a dice, those are independent events. When I flip a coin, the dice doesn't care. The dice doesn't care if it's head or tails. The probability of getting a 5 on a dice is 1/6, whether we get heads or tails. Those are independent events. Disjoint events are events that have no outcomes in common. Okay? So an example in a deck of cards, you draw an ace or a king. Well, there are no aces that are kings, and there are no kings that are aces. Walking around our school, the probability of picking somebody randomly that's an 11th grader or a 12th grader. Well, everyone that's in the school is in a grade. Now you may argue, well, there's retained the 12th graders, they're supposed to be in 12th grade, they're in 11th grade. But the point is they're in 11th grade. Okay, so you cannot be in 11th and 12th grade. Okay, you're either in 11th grade or you're in 12th grade. Okay, so those are disjoint events. Okay, so we have, I showed you some example of sample spaces. Okay, so what's a sample space for a rolling a dice? We could just go something like this. Okay, that's the sample space. Those are the possible outcomes. The complement of an event, okay, and that is the let's say that we have event A, like right here, and A takes up this much of this region, right? So let's say, I don't know, let's say it takes up 30% of the region. Well, the complement of A would be 70%. That would be the other 70%. So this is this whole region here that's not encompassed by that. Got it? Disjoint events are events that have nothing in common. So we have event A and event B. Those are disjoint. They don't have nothing in common. Now, if A and B were like this, those are not disjoint, because there is an overlap in here that A and B have in common. Those are not disjoint. Alright, so let's go through some concepts. The probability of something not happening. Let's say that we're looking at the probability of A. The way that you'll see this is you'll see the probability. Now this notation here means when you see a P with the parentheses in front, that means probability. So the probability of not happening is the probability of not A. And let's just say, for example, that the probability of A is 30%. Well, if A happened, what's the probability that A is going to happen? 30%. Well, what's the probability that A won't happen? Well, it's the other part of the 100%. Okay? It's like me saying, what's the probability of rolling a 5 on a dice? You'd say 1/6. Well, what's the probability of not rolling a 5 on a dice? You'd say 5/6. How'd you get that? Well, you do 1 minus the probability of it happening. So the probability of A not happening is 70%. The probability of not getting a 5 on a dice is 1 minus 1/6, which is 5/6. Okay. So the probability of A, example, is 0.3. The probability of not A is going to be 1 minus 0.3, which is 0.7. Okay. The probability of A or B if disjoint. Now the notation for A or B is A this way, B. It looks like a U, right? That means or. Okay, well let's take our dice example for example. What's the probability on a dice? Okay, we're going to get a probability of a 5 or a 6. 5 or a 6. First of all, are those disjoint events? Yeah, yes they are. Why? Because when you roll a dice, you can't get a 5 and a 6. 5 and 6 have nothing in common. You either get a 5 or you get a 6. There's no overlap there. So what's the probability of getting a 5? Well, it's 1/6. What's the probability of getting a 6? Well, it's 1/6. What's the probability when you roll a dice you get a 5 or a 6? Well, there's two outcomes, so it's actually 2/6. Okay, so how do we get that? Well, we add it. Okay, so the probability of a 5 is 1/6. The probability of a 6 is 1/6. So we do 1/6 plus 1/6 is 2/6. And if you wanted to reduce that, you can make that 1/3. So, what's the calculation? Well, if they're disjoint, it's the probability of A plus the probability of B. Or means we add, as long as they're disjoint. And we'll get into when events are not disjoint, but for now, we'll deal with disjoint events. Probability of A and B if independent. Probability of A upside down U, B. That means and. That's and. So U shape or upside down and. Okay. So let's take an example. Got two independent events. We're going to flip a coin. And we're going to roll a dice. Okay. So we flip a coin. We have two things that can happen. We roll a dice. We have 6 things that can happen. But when we flip the coin first, did that influence the dice? Well, no, the dice doesn't care what the coin did. So if I got a heads, what could I do? I could get a 1, 2, 3, 4, 5, or a 6. And if I get a tails, I could get a 1, 2, 3, 4, 5, or 6. Okay? So this goes there, 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 and this one goes here like this. So, let's see. So we're going to do the probability of a head and a 2 on the dice. Head and a 2. Well, let's see. Probability of a head and a 2. Well, there's 12 different things that can happen here, right? Here's our sample space. Head 1, head 2, head 3, head 4, head 5, head 6. Or I could get tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. There's your sample space for flipping a coin and rolling a dice. 12 outcomes. What's the probability of getting a head and a 2? Right there. Well, 1. There's only one time that happens. So it's 1/12. Okay? Well, what's the probability of flipping a coin and getting a head? Probability of heads here is 1/2. What's the probability of getting a 2? Well, if I roll a dice, the probability of getting a 2 is 1/6. So, if I know the probability of getting a head and a 2 is 1/12, then what do I do at 1/2 and 1/6 to get 1/12? Guess what? You don't add, you multiply. You gotta multiply. Okay. So this is the probability of A times the probability of B, only if independent. And you gotta know this. Okay. Somebody will say, what's the probability that it snows out and someone is late to school? Okay, well, those are not independent events. Okay, so you can't just say, oh, the probability of snow is 30% and the probability that somebody's late to school is 10%, so just multiply them. Well, no, you don't know that those are independent events. They're clearly not independent events, because if it snows out, it will affect the probability that somebody's late to school. So you can't just automatically multiply. You got to know that before you multiply. So what did we do? We did head and 2. So the probability of a head is 1/2 times 1/6, and we got 1/12. Okay, probability of at least 1. Okay, let's say that we're going to roll a dice 3 times. Okay, so we're here, we're going to do probability of at least 1. Okay, today we don't know how to spell, so let's see if we can do this. Okay, we're going to roll a dice 3 times. And we want to get at least 1, 2. So, whenever I roll a dice 3 times, how many results are possible? How many different types of results are possible? Well, the answer is there are 4. There's 4 different results that can happen if I roll a dice 3 times, and I'm looking for at least 2. At least 1, 2. Okay? I could get 0 2s, I could get 1 2, I could get 2 2s, or I could get 3 2s. Okay, so if we roll a dice 3 times, and we're looking for only 2s, there are 4 different results that can happen. We can get none, 1, 2, or 3. Each of these has a probability assigned to it, and by the way, they are not all equal. Alright, so these, by the way, are what kind of events. If I was to roll a dice 3 times looking at the different results, those are disjoint events. I can get 0 2s, 1 2, 2 2s, or 3 2s. Okay, but I cannot get any combination of them. So if they're disjoint events, I must add. So I add those. Well, if I add up all 4 results, those are the only 4 things that can happen if I roll a dice 3 times. So they must add up to 100%. Now, probability of at least 1. Well, what we could do is we could say, oh, okay, at least 1 is 1 or more. So I could add the probability of 1, the probability of 2, or plus the probability of 3. That's one way of doing it. So one way of doing it is to do probability of 1 plus the probability of 2 plus the probability of 3. And that equals the probability of at least 1. Alright? But there's another way to do it. I want to know that sum. Well, I say, okay, I don't feel like doing all that. What could I do? Well, I could subtract the probability of none from both sides. So the probability of 1 plus the probability of 2 plus the probability of 3 equals 1 minus the probability of none. So the probability of something happening at least once is 1 minus the probability that it does not happen. Okay? So the statistical notation is at least 1. Calculation is 1 minus the probability of none. And let's say that we take our example here and we want to do a dice 3 times, and we want to know the probability of at least 1, 2. Oh, we should make this 1, 2. Okay. Well, if I roll a dice, that means I got not a 2, and not a 2, and not a 2. And those are independent events, right? So not a 2, not a 2, and not a 2 is 5, 6 times 5, 6 times 5, 6. So I must have to do 1 minus 5, 6 to the third. That's the probability that we would not get a 2 3 times in a row. Okay, and if we do that out in our calculator, let's see if I can bring this up. 1 minus 5, 6 cubed. About 0.423. So the probability that we would get at least 1, 2 if we were to roll a dice 3 times is 42.3%. Expected number of successes, okay, is E sub x, not E of x. Calculation, okay. This one's pretty intuitive. If I was to flip a coin 100 times, how many times would you expect the heads to come up? Now, most of you said, well, 50. Well, how'd you get 50? Well, you did 1/2 of 100. Well, where'd the 1/2 come from? Well, 1/2 is the probability of getting a heads. So it's the probability of the event times the number of trials. So let's say that I was to roll a dice 60 times. How many times do you expect a 5 to come up? Most of you would say 10. Well, why? Because you're rolling a dice 60 times. The probability of a 5 is 1/6. So if you do 60 times 1/6, you get 10. So my first example with the coin, you did 1/2 times 100. That's the probability of a heads times 100, and you got 50. My example with the dice, probability of a 5 is 1/6, and we're flipping it, we're rolling it 60 times. Well, 1/6 times 60 is 10. Okay. Something you need to understand, these are theoretical. If I was to flip a coin 100 times, that doesn't mean the heads will come up 50 times. Theoretically, we expect it to come up 50 times. Okay, it may come up 52 times. That's okay. When we roll the dice, we expect the 5 to come out 10 times if we roll it 60 times. What if it comes out 12 times? That's fine. Remember, short-term anomalies could drown out in the long run. So, how do we do expected value? We do the number of trials times the probability. So, my example, if I flip a coin 100 times, the expected number of heads what's n? N is 100. That's the number of times we're flipping it. What's p? The probability, 1/2. So we would expect it, again, theoretically, to come out 50 times. Okay? Alright, let's look at problem 1. You got an 80% free throw shooter. Misses 10 shots in a row. What's the probability he makes his next shot? Well, this is the whole concept of what? It's law of averages versus law of large numbers. Law of averages, nonsense. Law of large numbers, statistically sound. So people sitting there are saying, what? Oh, he's due to make one. Now, the probability that he will make his next shot, the probability of a made shot would be 0.8. Doesn't matter what he did. How many free throws would you expect the shooter to make? Expected value, right? In the next 20 shot. Well, expected value is NP. What's N? 20. Probability of success, 0.8. So we would expect him to make 16. Again, that's theoretical. That also is an average. If we were to give him 20 shots, like 100 different times, okay, on average he would make 16 of them. Most of the time he would make 16 of them. Okay, but then there are times he would make 15, and there are times he would make 17, and then there are times he'd make 14, and there are times he'd make 18. Okay, so what this would wind up looking like is it would look like this. If we look at a histogram, this would be 16, this would be 15, this would be 14, this would be 17, this would be 18, and then 19 and 20 would go down further, and 12 and 13 would go down further to the left. Okay, so that's what that would look like in the long run if we were to give this person 20 free throws and have them do that multiple times. Okay, so we got the old shell game. There are 3 shells, balls hidden under one of them. Person guesses wrong 20 times in a row. What is the probability that the person guesses correctly the next time? Well, the probability of correctly guessing is 1/3 which is 0.3 repeating. How many times do you expect a person to guess right if they played 15 more times? It's just 15 times 1/3. On average, they would guess right 5 times. Alright, problem 2. Suppose that 40% of the cars are manufactured in the United States, 30% in Japan, 10% in Germany, and 20% in other countries. Cars are selected at random. Find the probability. Probability car is not a U.S. car. Well, the probability if it is a U.S. car is 40%. The probability of it not a U.S. car is 60%. Cars made in Japan or Germany. Well, are these disjoint? Yeah. Okay. German-made cars are made in one place. Japanese-made cars are made in another place. Now, they may have parts from different places, but that's not where they're made. So we got probability of Japan or Germany. So the probability of Japan, or means we add. Japan is 30%. Or means we add. Germany is 10%. And that's 0.4. You see 2 cars in a row from Japan. Well, if you see 1 car, does that influence what the other car will be? Well, assuming we're looking, we're not in Japan, we're in the United States, and we're looking at I-95, those are independent events. So we got a probability of Japan and Japan. And means we multiply. Probability of the first cars from Japan is 30%. Second cars from Japan is 30%. So that's 0.09. None of 3 cars came from Germany. Okay. So we got not German, not German, not German. Okay. Those are independent events. What one car is does not affect what the other car is. So we got the probability of not German and not German and not German. And means we multiply as long as they're independent, and they are. And not German, and not German is 0.9, 0.9, and 0.9. If we do that, I think it comes out around 0.72 something. 0.7, 0.9 cubed, 0.729. At least 1 of 3 cars is made in the United States. Okay. So the probability of at least 1 equals 1 minus the probability of not made in U.S. And these are 3 cars, so it's not U.S. and not U.S. and not U.S. Well, what's the probability of not U.S.? Well, it's 0.6. What's the probability the second one's not U.S.? 0.6. What's the probability the third one's not U.S.? 0.6. So it's really 1 minus 0.6 times 0.6 times 0.6, which is 1 minus 0.6 cubed. If we do that, we do 1 minus 0.6 raised to the third. And we get 0.784. And then the last one is the first Japanese car you see is the 4th one you choose. Okay. So that must mean, what was the first car? Well, it's not Japanese. Second car, not Japanese. Third car, not Japanese. It's the 4th car, Japanese. What goes in between these? And. First one, and second one, and third one, and the 4th one. Are these independent? Sure they are. What the make of one car is does not affect what the make of another is. So, and means we multiply. So not Japanese is 0.9. Oh, sorry, 0.7 times 0.7 times 0.7 times the probability is Japanese, 0.3. So we would do 0.7, 0.7, 0.7. So let's do that. 0.7 cubed times 0.3. 0.1029. And that's problem 3. Alright, let's look at problem 3 here. Suppose the weatherman predicts that over the next week there's a 50% chance it will snow once, 25% chance it will snow twice, and 5% chance it will snow 3 or more times. So, what is the probability that it will snow? Well, there's a 50% chance it will snow. So we're basically looking at what is the probability that it will snow at least once. So let's see here. We got 50% chance it'll snow once, 25% chance it'll snow twice, and 5% chance it'll snow 3 or more times. So that's really going to be 0.5 plus 0.25 plus 0.05. And that's an 80% chance that it will snow. That's an 80% chance that it will snow. So the probability that it will not snow is 0.2. What is the probability it will not snow more than once? Okay, so that it will not snow more than once. Okay, so the probability it will snow at least the probability that it will snow once is 50%. So the probability it will not snow more than once well, the probability that it will snow more than once is 25% plus 5%, so that's 30%. So the probability that it will not snow more than once is 1 minus the probability that it will snow more than once, so it's 0.7. Which, by the way, is your 50% chance that it'll snow once and the 20% chance that it will not snow. What is the probability of at least some snow? Some snow is a probability of at least once. And that's 1 minus the probability it will not snow. And that's also this 0.8 right here. Okay. Suppose the following week the weather conditions remain unchanged. What is the probability that over the 2-week period it will not snow either week? So probability of not snow and not snow. Those are independent events, so we just multiply them. Okay. So we just do 0.2 times 0.2, and that's 0.04. It will snow both weeks. So that's the probability of it will snow. There's an 80% chance of snow. So it'll snow and snow. It is 0.8 times 0.8, which is 0.64. It will snow at least one of the weeks. So at least one is probability of at least one is 1 minus the probability it will not snow either week. Well, the probability it won't snow is 0.04. So it's 1 minus 0.04 is 0.96. What must be true for questions 4 through 6? Well, this is and that's basically and, so the weeks must be independent. For us to be able to multiply. Is this reasonable? Around here it is. Generally we have weekly weekly weather events. Rain comes in, rain goes out. Snow comes in, snow comes out. So usually if you have a snowstorm on 2 separate weeks around here, it's usually 2 separate types of storms. So If you're in the Rocky Mountains, you might get a 2-week weather pattern. But for around here, I would say it would be a fairly reasonable assumption that those 2 weeks are independent events. All right, lastly, let's look at problem 4 here. So we got 1,092 people who are asked, what is the president's biggest issue? And they garnered the following responses. So if we add those up, we get 1,092. What is the probability the person thought that unemployment was most important? So the probability of unemployment equals 312 over 1,092. What is the probability the person thought federal deficit or health care? Well, are those mutually exclusive events? Well, yes, they are, because each person, the question was biggest issue, so you only got to choose one, so you couldn't go into multiple categories. So the probability of federal deficit or health care. Okay, federal deficit was 144. And healthcare was 84. So that comes out to 228 out of 1092. And what is the probability the person did not reply dissatisfied? The probability that they were dissatisfied was 108. So people who were not dissatisfied is 1092 minus 108, and that's 984. So the probability of dissatisfied is 984 out of 1092.